Okay, we've been talking chapter 2 here and got into kind of electrons obviously transitioning from different energy levels, the waves that come off that. But we got into quantum numbers and sort of the atomic orbitals and moving away from, again, Bohr's model of the atom, which is, again, that sort of planetary model where you have orbits and our electrons are sort of confined to these orbits as they rotate around. And again, the sort of colors and stuff that we see in terms of the line spectrum as a result of these electrons transitioning from one energy level to the next. So as time went on, a lot of things, sort of the dual nature of sort of particles and light, particles could have wave-like characteristics and waves could have particle-like characteristics. So we sort of moved away from the Bohr model to sort of a quantum mechanical type model where we talk about electrons really being in atomic orbitals. And again, those are our ones that we use for electron configuration, S, P, D, and F. We also, at the end there, sort of tied it together to quantum numbers, which is really the basis for example, why on certain energy levels, there's only certain, say, orbitals available on those energy levels and how many and so forth. There are 4 quantum numbers. There's n, which is the principal quantum number, and it's basically like the energy level, our principal quantum number here. It has values of basically 1 through 7. We have L, which is the angular quantum number. And really, you can think of L as describing sort of what atomic orbital is sort of present on that particular level. Remember, like an L value of 0 is S, an L value of 1 is a p orbital or subshell, and so forth. And it has values of 0 to n minus 1. So those are the values that you could have for any particular n value. You could have an L value that runs from 0 to n minus 1, all whole numbers. We have m sub L is a magnetic quantum number, and that's sort of how many orbitals there are. Really, it is sort of the three-dimensional sort of arrangement in space of those orbitals is really more so what it really is. And m sub L, for any L value that you have, you could have an m sub L value that runs from minus L to 0 to plus L, again, sort of whole numbers as you go through that. And lastly, we have our spin quantum number, which is basically can be plus or minus 1/2, depending on which way the electron spin is in the orbital. Remember that any individual orbital could hold a maximum of 2 electrons. So if we were to fill up the s orbital on any level, that's a maximum of 2 electrons. If we were to fill up the p subshell, which basically comprises of 3 individual p orbitals, that is 6 electrons. And obviously, if we filled up the d, which comprises of 5 individual orbitals, that would be 10 electrons. And obviously, if we did our f, that would be 14 electrons, again, as the f orbitals have 7 different individual orbitals. Again, each could hold a maximum of 2. Any questions on that there? So I think last time we did our kind of n equals 1. Remember that if n equals 1, L could really only equal 0. And again, the 0 is an s orbital. And again, our m sub L in that case would be 0. And our m sub s can be plus or minus 1/2. What that basically tells us, again, is on the first energy level, we pretty much have only a 1s orbital sort of present. When we go into the second energy level, n equals 2, we could have L values of 0 or 1, and that means that we could have s orbitals, and also our p subshell first starts to begin at that point. We could have an m sub L equal to 0 for our s, We could also have an M sub L of -1, 0, and +1, and that would be for our P subshell. So this would be for our S, this would be for our P subshell, and plus or minus a half. What that tells us is as we go to the second energy level, we will have a 2s orbital, and again, that is where we first start to see our P subshell basically take place. We get to the third energy level, which I think is where we left off. We could have L values of 0, 1, or 2. And again, that is S, P. And that again is our introduction of d orbitals on the third energy level. Obviously, we could have an M sub L for 0 for our S. We could have an M sub L of -1, 0, +1 for our P. And we also could have an M sub L for our d orbital of -2, -1, 0, +1, and +2. Again, if you add up all those numbers or how many numbers there are, not necessarily add them up, that's 5 different numbers, and each one represents one of the 5 different d orbitals that are within that subshell. So that's what tells us that on the third energy level, we again have our s orbital. We also have our p orbitals. And again, this is our first introduction to where d orbitals basically occur, and that should be 3p there. And obviously here, n equals 4, if we were to kind of continue that pattern, L could have values of 0, 1, 2, and 3, S being 0, L being, or 1 being P, L value of 2 being D, and an L value of 3 is going to be our F orbital. So this tells us that when we do get to the fourth energy level, we would expect F orbitals to first start to appear. Obviously, here we could run an M sub L for each of those equal to 0, just like we had above, -1, 0, +1 for our D, -2, -1, 0, +1, +2. And now for our F, go up for F, would be -3, -2, -1, 0, +1, +2, +3. And that again, if you count up how many numbers you got going there, that's going to be 7 different numbers again for our 7 different F orbitals. So on our third energy level there, our fourth, 4s, 4p, 4d, and again here 1, 2, 3, 4, 5, 6, 7, and then we have our 4f. Any questions on that there? Now, what happens when you kind of keep going, like you get to the n equals 5 level, for example? You could have L values of 0, 1, 2, 3, and 4. And we already know that's an S, that's a P, that's a D, that's an F. What would the next one be? It actually just goes alphabetical at that point. So that'd be like G, come next, and so forth. So not that you'll ever get to that for any type of electron configuration, but it just sort of goes alphabetical after F if you know how to give a label for those type of orbitals. Any questions on any of that there? So clearly, the way electrons go into the atom is they will go into the lowest energy level first and fill up, and then they'll go to the next and fill, and the next and fill, and so forth. So it will continue to fill this way, and this is what allows us to write electron configuration. And when you have something like hydrogen, for example, that has this one electron, all of the orbitals on a particular energy level, which again is sometimes referred to, as we also talked about, a shell or a level. Remember that if you just take, say, like a 3p subshell, that's a group of p orbitals together. All these guys will be equal in terms of energy. But once we move away from something like hydrogen that has more than one electron involved, when you get a lot of electrons involved, electrons are negatively charged, which means ultimately they do not really want to be near each other because they have the same charge, but they can escape. So they have to sort of do that. And what happens when we get a lot of electrons sort of involved is there's actually a switch or a change that occurs in terms of the energy level of our orbitals. And that obviously affects how electrons go in. The order actually is pretty similar here. It's 1s, then 2s, and 2p is actually a little bit higher than the 2s, 3s, 3p. And this is really where the main difference sort of occurs is actually the 4s orbitals actually end up being lower in energy than the 3d orbitals. And that means that when electrons get, or when atoms get electrons or electrons go into the atom, they will actually fill the 4s electrons first and then go to the 3d. And that sort of pattern of S before D also kind of continues to happen as you continue down that path. So there is an order at which electrons go into the atom that you could write electron configuration. And as we talked about, a couple important things for electron configuration is obviously knowing what we talked about. S is a maximum of 2 electrons, P subshell 6, D subshell 10, and our F subshell being 14 in that case. So knowing how many electrons that you can max out in and knowing the proper order is really important. So there is one way that you could kind of figure out the order for yourself, and it is based on what we just talked about, which is essentially on the first energy level, there's only s orbitals. It's not until the second energy level, kind of go down to the right, that p orbitals begin. And it's not till the third energy level, go down to the right there, that d orbitals appear. And it's not till the fourth energy level that f orbitals appear. Now, if you remember that, you basically can make your own sort of order at which electrons go into the atom by just putting numbers underneath it with the letters. So you could go like a 2s, you go a 3d, 4d, 5d, 6d, 7d. We go 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, and 4f and 5f. So this is basically the order at which electrons go into the atom. As you can see, there's pretty easy to sort of remake it for yourself on a piece of paper. We always start up here, and we basically kind of go until we fill up an orbital, our subshell, and then we zigzag back. So as you can see here, heading in this direction. And here we do see, I wrote D's on this. That would be better if I wrote S's, though I did actually. Kind of like S's there. You probably should write the right letter all the way down there. Try that again. Like, wait, that don't look right. 3S, 4S, obviously 5S, 6S, and 7S. There you go. All right, that looks a little better now. Obviously, use the same letter all the way down. So we can see here our 3P and then our 4S, and then we come back to our 3D. And once again, you can see here we have our 5S and then our 4D and so forth coming through. So again, you can see that pattern of really the S before the D does continue to happen. So if you know pretty much this and you know this, you can write any electron configuration that you would need to do. So let's write some of them here and go through and make sure. So if we start with hydrogen, which is atomic number 1, which has 1 proton, and obviously if it is neutral, it will also have 1 electron, right? So that's all it's got. So again, we start up here always, and it would be 1s1, which is the way that you would say it. It is the first number here is the principal quantum number, that n number. That is obviously the orbital or subshell it is in. And this is the number of electrons in that orbital or subshell. So basically what we're saying here is on the first energy level in the s orbital, we got 1 electron basically hanging out there. Now, there's another way that we sometimes represent electron configuration, and that is what is known as orbital diagram. An orbital diagram uses boxes or lines and arrows to represent electrons to kind of visually show electron configuration. So if we did it for hydrogen here, we would need one box. I'm just going to use a box, and that would represent my 1s orbital. And when we throw our electron in there, it will always point in the upward direction, our first electron. And that would be the orbital diagram there for hydrogen. Now we can assign our 4 quantum numbers to this electron. What should the n value here be? N is equal to 1. That's what that first number means. So it's on the first energy level. If n equals 1, L will equal 0 in this case, and it does because it is a s orbital our electron's hanging out in. And that means that in this particular case, because L is 0, our m sub L could also only be 0, which is what it would be. And our m sub S in this case is actually plus 1/2. Again, not plus or minus in this case, because we're specifically talking about this electron, which is heading in the upwards direction, which means it has positive spin. So remember that if an arrow is kind of pointing upwards, that's positive spin. And if it's going downwards, that is negative 1/2 in terms of the spin quantum number. Any questions on that? So that brings us to our friend helium, which is number 2 on the periodic table. That means it has 2 electrons. We once again always come back here and start, and that would mean we would have 1s2 in this case. Now, if we draw our orbital diagram here, we again would need a box or a line to represent the 1s orbital. We know that our first electron will go in the upwards direction. We actually have a couple of options here in terms of how we might want to put that second electron in. We obviously could go in the same direction. We could go in opposite directions. This is what is sometimes referred to as parallel spin. And this is what is sometimes referred to as paired spin when they're going in opposite directions, electrons. So there is a really important rule that helps us decide how the second electron should go into it, and that is our friend Pauli's exclusion rule. And Pauli's exclusion rule basically says that no 2 electrons in the same orbital can have the same 4 quantum numbers. So if you have 2 electrons in the same orbital, they cannot have all the same quantum number. So clearly we just did our quantum numbers for this first electron, right? Which is right here. Again, n equals 1, L equals 0, m sub L equals 0, and m sub S would equal 0. If I went with my first option here, which is put my electron heading exactly the same, what would be the quantum numbers for this electron? It would be exactly the same. N would equal 1, L would equal 0, M sub L would equal 0, and M sub S would equal plus 1/2. That is a clear violation of Pauli's exclusion rule. They cannot have the exact same spin. I'm sorry, they cannot have the exact same 4 quantum numbers in the same orbital. That means that when 2 electrons share an orbital, an individual orbital, which is the maximum number of electrons you could put in there, they need to go in opposite directions in terms of their spin. That means that our second electron that we would put in here does need to go in pointing downward. And as I mentioned before, this means that the spin is paired. And if we did our 4 quantum numbers for this guy pointing downward, N would equal 1, L would equal 0, M sub L would equal 0, but the difference here is the spin is going to be minus 1/2. So that difference in the spin between the first electron and the second electron will give them 4 different quantum numbers. They won't share the same 4 quantum numbers. That means they will not violate Pauli's exclusion rule. And that is always how 2 electrons go into the same orbital. First one always goes up. Second one goes down, opposite spin. And that's basically why they're called paired spins, because they kind of cancel each other out. One's kind of plus half, minus half. They sort of cancel out their spin production there in that particular orbital. Question on that there. Okay. So let's continue on then and take a look at our next one, which is lithium. Lithium is 3 electrons. It's got 3 protons, so a neutral lithium would have 3. Once again, if we're going to write the electron configuration, we're going to come back over here. As we could clearly see at this point, we cannot put any more electrons in there. So we will have to go here and again, then zigzag back down to here to our 2s. So that means that we would have 1s2, 2s1 in this particular case. If we look at our orbital diagram, we will need 2 boxes, one for the 1s and one for the 2s. Now, normally, if you were going to draw this based on energy, the 2s should go above the 1s. I'm just going to draw them next to each other to save space. But if you're going to do it kind of based truly on energy, obviously my 2s is higher in energy than my 1s. It should go above it. We're going to put our first electron in, second electron in, and now our third electron will go into the 2s orbital and will go in this upwards direction. I have how many electrons on the first energy level? I have 2 on the first energy level, right? And on the second, I have 1 electron right there. The quantum numbers for this electron, n is equal to what? N is equal to 2, right? It's in the 2s orbital. That means that L could have values of 0 and 1. Are they both correct in this case? They are not both correct because that electron is hanging out in what orbital? The s or the p? It's actually hanging out in the s. So specifically that electron, the only L value it could have is 0 in this case because 0 represents the s orbital. P orbitals are available, right? Because we're on the second energy level. We just don't have electrons in them at this point, but they are available. So we're talking specifically about this one electron here. It has to be an L value of 0 because it's sitting in the s orbital. Questions on that there. Now m sub L, because our L value is 0, the only option is 0. And our m sub s here is going to be plus 1/2 in this case. Any questions on those there? Now rolling to our next one, which is beryllium, which is 4. That's going to give us a 1s2, 2s2. And once again, this is how it's supposed to be written. No dashes, no commas, no big numbers. So superscript, regular number. In this case, we have how many electrons on the first energy level? And on the second? Yeah, we have 2 on both of them, right? We'll look at our orbital diagram here, and we'll have a 1s box and a bigger 2s box for some reason. We'll go up, we'll go down, we'll go up, and then obviously here, our newest electron will go down. Now, if we did our quantum numbers for this guy, our n would equal 2 because it's on the second energy level. Our L here would equal 0, right? Because it's still in the s orbital, so it cannot have a value of L, which would be the p. That means our m sub L here going to be 0, and our m sub s will be minus 1/2. Any questions on that there? All right, let's continue through a first few here. I'll go 5 there, which is boron. So once again here, we are going to roll back to our starting. We will go 1s. We just filled our 2s. We now got to zigzag back to our 2p, in this case, the 2p subshell. So that's going to give us a 1s2, 2s2, 2p1 in this particular case. We have how many electrons on the second energy level? I'm going to go with the fingers you held up, which is 3, I think, is what you held up there. Are you just saying, okay, I'm not sure. But that is 2 and 1. Either way is good. That is 3, right? If we add up the top numbers, we still have our 2 there on the first energy level in this case. Now, if we go for our orbital diagram here, again, just drawing it side by side, not energy correct. For our P, which is a P subshell, we would actually need 3 boxes or 3 lines to represent each of the 3 orbitals that are present in this case. We're going to go up, we're going to go down, we're going to go up, we're going to go down, and the first one will come over here in this particular case. Now, if we were going to do our quantum numbers for this electron here, n should equal what? 2. L should equal. So once again, L in this case could have values of 0 or 1. Which one is the correct one in this case? It is 1, as that represents a p orbital, right? So that is what it is. Now, because L actually equals 1, we could have an m sub L that is -1, right? 0 or +1. And just like, because we're talking about a specific electron here, we are talking about a specific orbital it's in. By the way it goes is just like this, left to right, -1, 0, +1. That means the m sub L, the electron is in the -1, yeah? So it just kind of goes left to right in terms of the numbers, just like you give them. And that puts it in there, which is really, in this case, the px orbital. That's the py orbital. That's the pz orbital there, that third one that's happening there. And in this case, our m sub s is going to be +1/2. Any questions on that? So you should start to see here that you can use quantum numbers specifically for specific electrons. You could give the 4 quantum numbers for those specific electrons. You could also, as we kind of did last time, just generically talk about an energy level and what's available on that energy level in terms of quantum numbers. So you can get pretty specific in terms of the quantum numbers. So let's take a look at the last few here on this first period or second period. We'll go carbon next, which is 6. So again here, we're going to start at the top, 1s2, 2s2, and now we're going to go 2p2 in this case, which if you count up the top numbers, 2, 4, 6, which is our electrons. We will roll through here with our orbital diagram. So up, down, we went up. We now also have, in this case, some options as to where you might want to put the next electron. So if we look at a subshell like the 2p that has multiple orbitals, we could pair it off. We could also put it in the next orbital over. And there is another rule that helps you decide that. We'll go with Hund's rule. Why not? Sounds like a good one. Maybe I'm making it up. I don't know. Hund's rule. And he says that the maximum stable position is to sort of maximize parallel spin. So remember, parallel spin is when they're all heading in the same direction. Paired spins when they go one direction one way and one the other. So what that means is, based on Hund's rule, we would not want to do this. And when you have a subshell that has multiple individual orbitals, you always want to maximize parallel spin, which means we would fill up everybody with one going in the same direction till we run out of room, and then we got to go back and start pairing. So that is the rule. When you hit multiple orbitals in the same subshell, you will pair them up, not pair them up, you will go parallel spin, and then when you run out of room, you will then start pairing. Any questions on that there? Again, if we do our quantum number here for this electron, why don't you do it? What is the quantum number for that electron, right? The 4 quantum numbers. Okay, so let's take a look. So hopefully we know this is our n number. So n does need to equal 2 in this case. That gives us, once again, a option of 0 or 1 for L. And since we're specifically talking about that electron, that is also in a p orbital. So L here has to be 1 in this case. Remember that we have a choice of 3 orbitals it may be in, the px, py, and pz orbital, which basically kind of goes this way in terms of our m sub L number. And that means that it's actually hanging out in the 0 orbital, or the py orbital. And it is heading in the upwards direction, which means the spin quantum number is plus 1/2. Any questions on that there? We'll look at, we got their nitrogen next, I think. So nitrogen, and obviously if we look here, before I scribbled in it, we got room for 2, 3, 4 more electrons, obviously, right? Before we have to move on from the p subshell in this case. So going to nitrogen, which is 7, we again would have 1s2, 2s2, 2p3 in this case. Once again, if you count up the top numbers, 2, 2 is 4, plus 3 is 7. We have 5 electrons on the second energy level. We have 2 on the first energy level. And if we look at our orbital diagram here, go up, down, up, down, up, up, and obviously we have one more option for up, which will maximize the parallel spin in this case. And again, if we look at quantum numbers, n would equal 2, L would still equal 1 as it's sitting in a p orbital. M sub L, we're now talking about the guy that has gone all the way to our pz orbital, which is plus 1. And it also has a plus 1/2 spin. Any questions on where I got any of those numbers from? All right, let's finish up the first 10. Why not? We'll do oxygen, which is 8. So we can go 1s2, 2s2, 2p4 in this case. And looking at our orbital diagram here, 1s, 2s, 2p. So up, down, up, down, up, up, up. And again, we come back to the first one there. And now, since we have no choice, we're going to pair off that last electron. And in terms of quantum numbers now for this guy, n would equal 2. L would still equal 1 as it's in a p orbital. M sub L in this case has now moved back to the very first one, which is -1. And in addition, it's paired to spin, which means its spin quantum number now is -1/2. And obviously not +1/2 like our first electron in that particular orbital. Questions on that one there? Then let's do 9, which is fluorine. That's going to be a 1s2, 2s2, 2p5. Once again, if we count up just the top numbers, that will give us our total number of electrons we put in, which is 9 in this case. We got 7 on the second energy level and still 2 on the first in this case. Looking at our orbital diagram, 1s, 2s, and our p here. So up, down, up, down. We're going to go up, 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 down, and that last one there is going to go down. That will give us an n value of 2 since it's on the second energy level. Once again, our L value will not be 0. Our L value will be 1, which is a p orbital. Here again, -1, 0, +1. That means our m sub L will actually be 0 in this case. And our spin is going downward, so -1/2. Any questions on that one there? And lastly here, we'll go with neon to finish out the first 10. And that's going to give us 1s2, 2s2, 2p6. And that should completely fill us up here. So up, down, up, down, up, 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 down, down, and lastly down here with this being n is equal to 2, L is equal to 1, M sub L is plus 1, as it's minus 1, 0, plus 1, and M sub S in this case minus 1/2. Any question on how to write electron configuration, draw orbital diagrams? And by the way, when you're asked to draw an orbital diagram, it is this, boxes and arrows, not like the circle and the figure eights or anything like that. People always draw like those guys for that. And also be able to figure out the quantum numbers for any electron. Any questions? All right, why don't you try, I don't know, why don't you try, do why don't you do calcium, which is 20. And why don't you give the 4 quantum numbers for the, I don't know, let's do the 16th electron that goes in. So write the electron configuration, draw the orbital diagram, and give the 4 quantum numbers for the 16th electron that's in calcium. Okay, so let's take a look and see how we're doing. So we got 20. So again, we always start at the top of our sort of chart. So we're going to start with 1s2, 2s2, 2p6. Again, if we count up the top numbers there, that is 10, which means we've got a few more to go. We then would go, as we zigzag back there, to 3s2, that is 12. And then 3p6, that is 18. Remember, after 3p, before 3d, it is the 4s that slips in there and sneaks in, and that is the 4s2 comes next, not the 3d. Once again, as those orbitals rest, the 4s actually is lower in energy than the 3d. So it does go to the 4s first. We'll also talk about shortly what happens once we start putting electrons here. It actually does a little switcheroo back in terms of energy. But as they get filled, the 4s actually is lower in energy first. Any questions on electron configuration there? That means for our orbital diagram, we would need a box for 1s. And again, I'm not going to do it based on energy, just going to try to save some space, go sideways here. We'll go with our 2p. We will need 1 box for our 3s. We'll need, again, 3 boxes here for our 3p and 1 box here for our 4s. So we're going to go up, down, up, down. Remember, these will go in one at a time and then come back and fill. Up, down on that one. Again, one at a time. And then fill. And up and down in that case. Any questions on that there? Now we're looking for our 16th electron. So that is 2, 4, 10, 12, 18. So I'm feeling like it's in the 3p subshell, right? My 16th electron. So coming into my 3p subshell, I got 12 working for me. This is why it's important the order at which they go in, right? So if that is my 12th, then this should be my 13th. Next to it there in the next orbital should be my 14th, right, as they go in one at a time. This should be my 15th, and my 16th will actually go back to here, right? So that right there should be my 16th electron. So again, that's why it's important to understand again the way that if they do fill, so you just don't count like 16 straight across, right? Any questions on that? So that means that my end value for that electron should be what? An end value of 3, right? It's hanging there in the 3p orbital. Because n could equal 3, all the possible L values would be 0, 1, and 2, but we're specifically talking about that electron, and that means the only L value that should be is 1, right? Because again, it's in a p orbital, and that is what the 1 represents. The 0 represents an s orbital, right? So it can't be an L value of 0 because it's not sitting in the s orbital. The 2 in this case represents what orbitals? It represents the d orbitals, right? And obviously this guy's not sitting in the d orbitals, right? So again, that's why we can't just put 0, 1, and 2 as they all represent different orbitals. And we're specifically talking about this one electron and where it's hanging out. That means that our M sub L will be, again, options of -1, 0, and +1. Once again, it goes in order, -1, 0, and +1. That means we should have a -1 there for our M sub L. And our spin should be plus or minus a half. In this case, it should be minus a half as it's pointing downward. Any questions on that right there? All right. Now, in addition, when we look at this configuration that we wrote up through here, that is how many electrons? That is, we count the top numbers, 2, 4, 10, 12, 18 electrons in green. If we go to periodic table, number 18 is our friend argon. Yeah. And argon is part of group 8 on the periodic table, which are the noble gases on the periodic table. And we could write a shorthand for electron configuration where we put argon in brackets, and that indicates the electron configuration for argon. And you can continue on with 4s2 if you like, and that is sort of a shorthand. Sometimes people will call it a noble gas configuration. I'll write it up here so you can see a little better, maybe 4s2. Again, that is what is in green over here, basically. Yeah. So that's another way that we can write electron configuration. Again, if we kind of have a shorthand, it does has to be when you go bracketed, whatever's in the bracket, it does need to be a noble gas. So it does need to be a noble gas that goes in there. And again, that is group 8 on the periodic table. The very last group there, helium, neon, argon, krypton, and so forth. And again, you would just continue on with the electron configuration to do that. Any questions on that there? Now, in addition, obviously here, if something has a charge, we do have to adjust the electron configuration. So for example, if we had sodium with no charge, which is 11, its electron configuration would be 1s2, 2s2, 2p6, 3s1. Now, when sodium makes a charge, it will make a +1 charge. The plus, as we talked about, means that it has lost electrons, and +1 means it's lost 1 electron, which means our friend sodium here will actually have 10 electrons with a +1 charge. That means its electron configuration is 1s2, 2s2, 2p6 would be the electron configuration for sodium ion that has a +1 charge. By the way, that is 2, 4, 10. Who on the periodic table is 10? That is also neon's configuration, right? Now, we could have something like oxygen. which as we did earlier has 8 electrons with no charge, 1s2, 2s2, 2p4. When oxygen gains a charge, it will make a -2 charge. Minus means it has gained electrons. 2 is how many it gained, which means it will have 10 electrons. 1s2, 2s2, 2p6, also 10, which is neon's configuration. That is really the whole point of bonding, as we'll talk about in the next chapter, is really for everybody to end up like the noble gases in terms of electron configuration. That's the whole purpose of bonding, be it ionic bonding, be it covalent bonding, where they share electrons, where they transfer electrons. The goal is for everybody to have the same electron configuration as the noble gases. That is because, as we'll talk about, the noble gases are stable. They're chemically inert. They're quite happy. And everybody wants to be like them. And that is how they do it, by losing electrons, gaining electrons, or sharing electrons to do so. You can see on the periodic table, if you look where sodium is located, where oxygen, not drawn to scale here, is located, and neon is located. Metals will lose electrons and end up back at the noble gas that comes right before them. Non-metals will typically gain electrons and go forward on the periodic table to the noble gas that comes after them. When you talk about electron configuration of oxygen with a -2 charge, or oxide ion, sodium ion, or neon, they all have the same electron configuration. They are sometimes referred to as being isoelectronic with each other. Things that are isoelectronic are things that have the same electron configuration. The bonus question here is, does sodium with a +1 charge become neon? Does it become neon? It does not become neon. It is still sodium, because the important subatomic particle that determines what element it is, protons, electrons, neutrons, which one determines? It is protons, the atomic number. So here we're only changing electrons, not protons. So it is still sodium, but it has the same electron configuration as neon, which makes it quite stable in that case. So sometimes people think, oh, it just like becomes that. And remember, it cannot become that unless you do something with the protons, which in a normal chemical situation, not nuclear chemistry, that doesn't happen. So we don't play with anything within the nucleus. Any questions on that? So if I had aluminum with a +3 charge, what would be its electron configuration? And if I had Br minus, what would be its? Okay, so let's take a look. Aluminum with no charge has 13 electrons. This has a +3 charge. Again, the plus means that it has lost electrons, and it has lost 3 electrons from its neutral guy, which means our aluminum with a +3 charge should have our 10 electrons in this case, which means its configuration would be 1s2, 2s2, 2p6. And we could actually add that to this list of another one that is isoelectronic with the rest of them that we did there. That again is neon's configuration in this case. Any questions on that one there? Bromine, which is 35, no charge. Here with a -1 charge, minus means that it has gained electrons. 1 is how many it gained, so that's going to add 1 there. It's going to have 36. And that is going to be a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And I ran out of room there. But I am up to now 10, 20. So I got a little bit more to go. I'm going to go underneath since I ran out of room there. What comes after 4s? After 4s should be 3d10. That now pops me to 30, I think. And now I need a 4p6 in this case, right? To take me to krypton configuration, basically. Yeah. So again, in this case, bromine gains one electron, goes forward on the periodic table to the noble gas that comes right after it. Here we see aluminum back up 3 spots there, back to the noble gas that came before it, which is neon. Any question on that there? By the way, speaking of these electrons, there are different types of electrons. This right about here is the highest energy level electron, right? And there's only one, by the way. That is what is known as valence electrons. Valence electrons are the highest energy electrons. They are really the ones that are furthest away from the nucleus. They're not held as tightly, and they're important because they are the ones that are involved in bonding. As we'll talk about when we get to bonding, they are the valence electrons. The lower energy level electrons are sometimes referred to as core electrons. Core electrons are closer to the nucleus. They're held tighter because they're closer to the nucleus, and they're usually not involved in bonding because of that. It's like energy inefficient to try to rip up an electron out of the core. It's very hard in terms of energy for that to happen. Any questions on things with charges? Noble gas configuration, any of those things? All right. So we kind of bounced around a little bit and did some of the stuff there. So we're just gonna kind of go through some of these and we'll pick back up at some point there, maybe. A lot of empty pages there. There it is. So obviously, I think we did this one actually last time as we were kind of cruising around. But again, principal quantum number of n is equal to 3, determine the number of allowed subshells, the L values. So obviously with an n is equal to 3, L could go from 0 to 1 to 2, which would represent our S, our P, and our D orbitals on the third energy level. Again, L could go from 0 to n minus 1. So in this case, n is 4, so 4 minus 1 is 3. That's where it will max out in terms of its L values. Any questions on that one there? Again, I think we did that one maybe last time. All right. Now for an L value of 2, the M sub L again would go from our minus L to 0 to positive L. And again, that's our minus 2, minus 1, 0, plus 1, plus 2. This represents basically the 5 different d orbitals in this case, right? In this particular subshell. And again, if you sort of drew orbital diagram box-wise, it would just go basically kind of in this order, basically, if you had to sort of give a number for each of those, yeah. Right. Like we did that we went over. Wonderful videos, you remember. There we go. So we'll skip through these again. Still a clover leaf. I play still a donut, I think. There we go. There we go. We got into that there. We talked about obviously our spin quantum numbers and our Pauli's exclusion rule in this case as we were going through our electron configuration. As we talked about as well, atoms with more than one electron, again, that pathway is unknown, and a lot of the negative and negative attraction does sort of move around our orbitals as we talked about, which gives us a special order at which we should put electrons into the atom. And that means that in some cases, some of the orbitals will penetrate further closer to the nucleus than others. So again, our 2s will be lower in energy than our 2p as it gets closer to the nucleus. And that's what we see with our 4s to say our 3d. The 4s actually is able to penetrate closer to the nucleus based on its wave function than say the 3d, which again is why we put those electrons in there first into the 4s. So again, you can see here the kind of purplish guy. We got our sort of 2s penetrating in closer than our 2p orbital in terms of its distance from the nucleus and probability. And also, as you can see here again, we can see our 3s first, our 3p, and then really our sort of 3d penetrates sort of the least there in those sort of comparison. And again, that's why the order is like 3s, 3b, 4s slips in there, and then our 3d. So let's talk a little bit about the periodic table as well, and we're going to talk about transition metals as well and sort of their electron configuration. But let's kind of officially talk about the periodic table here. It was obviously originally constructed to put, elements that have similar sort of properties together within groups and periods. They also left off some spots along the way and kind of filled it in. When we look at the periodic table, there are important things. All right, so here's periodic table, much better than my bad drawing. And when we look at the periodic table, there's a couple of things as we talked about the other day. We do have groups, and groups go up and down on the periodic table. And as you can see on this particular periodic table, even the one that's hanging up on the wall there, there's a lot of different numberings that you sometimes will see. Sometimes there's the A numbering, sometimes there's the B numbering, and sometimes they just number 1 through 18 as well. Typically, in most chemistry classes that you use or take, we use the A numbering, which is the representative numbering. So this is group 1 here. This is group 2. We do skip, and this is group 3, 4, 5, 6, 7, and 8. Most people just call it groups 1, 2, 3, 4, 5, 6, 7, 8. Most people don't include the A in terms of it, but that's usually the numbering that we take. We do kind of skip out the middle there. A reminder as well, as I might have mentioned when we were doing the experiment the other day, group 1 actually starts with lithium. So even though that hydrogen is hanging out there on top of group 1 on most periodic tables that you see, group 1 does start with basically lithium. There's also periods. Periods head in this direction on the periodic table. So there are 7 periods going this way as well. So groups up and down, periods left to right on the periodic table. Now, as we also talked about previously, not too many people call them families anymore. Most people call them groups, unless you're really old like me. When we look at this periodic table, we also talked about the top number. That is our atomic number. And again, as we talked about in chapter 1, that is our number of protons there are in that atom. Once again, the bottom number is actually the atomic mass. Again, not the mass number, but the atomic mass that you see there. When we look at the periodic table, it is basically broken up into sort of 3 parts. There are metals, there are nonmetals, and there are semi-metals. And usually on most periodic tables, people draw the staircase. As you can kind of see on that one, they kind of drew it in pencil-ish or so. But usually right around boron, you'll see this sort of staircase action happening, kind of coming down. And to the left of the staircase, those are metals. To the upper right of the staircase, those are nonmetals. And actually right on the staircase itself, those are what are referred to as metalloids or semi-metals, they're sometimes called. Metals are good conductors of heat and electricity. They can be, typically will have shiny appearance. They can be pulled into wires. Pretty much most metals are solid at room temperature. The one exception is mercury, which is why mercury a lot of times is like a different color on periodic tables. Hg, it's kind of bluish on most periodic tables. It is actually a liquid under kind of standard conditions. Now, nonmetals, on the other hand, have pretty much the opposite sort of characteristics. They are dull, they are brittle. They also are bad conductors of heat and electricity. They basically will have kind of the opposite characteristics of a metal. They also will have a lot more variety in terms of the state at which they are in. So some nonmetals are gases, some nonmetals are liquids, and some are solids. Most nonmetals are those diatomic elements, or I guess the way to say that, the diatomic elements that we've talked about previously, which are elements and also molecules. They're pretty much all nonmetals. So these are all nonmetals. All those halogens we played with in the experiment the other day, those are all nonmetals as well. Um, this is also why when we look at the periodic table, this guy right here is hydrogen. This guy's lithium. What type of element is hydrogen? Hydrogen is a metal, non-metal. It is a non-metal, yeah. So even though it's hanging out over here with all its metal friends, it's actually a non-metal. And that is why all the rest of it in group one here, they're all metals. And that is why group one starts with lithium and not hydrogen, which is a non-metal. The reason why hydrogen's over there is pretty much, even though it's not a non-metal, it has some characteristics that in certain situations, it kind of acts like a metal. And it has some special properties that we'll talk about. Older periodic tables actually would throw a lot of times hydrogen on both sides. You sometimes see hydrogen kind of located in both areas. Right on the staircase there, just to overlay in some books, I don't recall off the top of my head if your book does or not, but some books will include boron with it as well. Will give us our semi-metals as you kind of come down, this way here. We have some antimony and so forth. What are semi-metals or metalloids? They are actually elements that really, if you just look at their location, they're between metals and non-metals. So these guys have characteristics that also fall on both sides. So the same element can have some characteristics that most people would consider a metal characteristic, and that same element can also have some characteristics that will be like a non-metal. So a lot of like semiconductors and stuff like that are in that sort of area. In addition, there are certain groups on the periodic table which have certain names. Group one, which starts with lithium, that is known as the alkali metals. Right next door where beryllium is, magnesium and so forth, that's the alkaline earth metals. By the word alkaline means basic, pretty much. And in group one and group two on the periodic table, that is where a lot of our kind of strong bases actually come from. Things like sodium hydroxide, potassium hydroxide. So a lot of bases kind of come from group one and group two on the periodic table. We head down over here to group seven, which we looked at the other day. Those are our friends, the halogens, is group seven. And right next door to group seven is group number 8, and those are our noble gases. As I mentioned before, noble gases are sometimes referred to as being chemically inert. They pretty much will not react with other things, but they will react with themselves. And it is pretty much, they're very, very stable. And that is ultimately, as I mentioned, pretty much what everybody's trying to achieve through bonding is to end up with the same electron configuration as our noble gases. In addition to those areas on the periodic table, the area between group 2 and group 3 on the periodic table, those are our transition metals, which are pretty much in here. And our transition metals, as you may remember, maybe from your previous chemistry class, those are the guys that most often have a variety of charges. In certain cases, for example, iron could be +2 or +3. Other cases, for example, copper could be +1 or +2. So those are guys, for example, that you use Roman numerals when you name them and stuff like that. If you follow the atomic number on the periodic table, we go 5772. The missing row right there is right there. That's 58. And if you go underneath, that's 89 and like 104. This guy goes there. These two rows here actually technically go right there on the periodic table. And that's what's known as the lanthanide and actinide series for the two elements they should follow on the periodic table. They're also sometimes referred to as intertransition metals because technically they kind of go in the middle of transition metals. I've only been in one place ever that has the periodic table like that. It takes up the whole wall because it got to shift the entire periodic table all the way to the right. So that's why they actually will put it on the bottom in most cases So your periodic table, like in your books, is not like 4 pages wide or something like that, because it has to fit all those guys in there. Question on the periodic table. So you need to know obviously where metals are, non-metals are, and metalloids are. You need to know characteristics of each of those. You need to know which way groups go, which way periods go. You need to know the group numbering of 1, 2, skip the middle, 3, 4, 5, 6, 7, 8. And you need to know where the alkali metals are, the alkaline earth metals, halogens, and noble gases, and obviously transition metals are. Any questions on that there? Okay, so this is a good stopping place for